Alright, my name is Caleb Grant. I am again recording my Physics 1 Lab 3. So yeah. So what I did was I went out and took a video of this car on my phone. As you can see, the car is coasting nicely along the street. If you want to see that again, I will let you. There you go. Coasting nicely. Slope here, it's a very constant slope and not a whole lot changes, so the velocity is constant. Yeah. So what I did was I went and took that data and put it in the spreadsheet, and then took the first 3 points here and calculated an instantaneous velocity from that, and went into my model and put that in as the initial velocity for the model point mass. Changed the delta t to more accurately simulate the tracker software, and changed the initial position to again more accurately simulate what was in the tracker, and the time again more accurate simulation. And then I ran that, which, should it decide to go today, the ball jumps off the screen, creates this nice straight line here, which is all really boring because it doesn't really show much. But when you go to here, this is the model data, this is the tracker data, and as you can see, I'm looking at centimeters per second, all that's data in centimeters per second. As you can see, they end up very close to each other. The model predicts the car will end up at 258 centimeters from the origin, whereas the car actually ends up at 262 centimeters from the origin, so that's pretty good. The velocity is 488 centimeters per second for the tracker software and 485 centimeters per second for the model. So when those are plotted on the same graph, position versus time, blue for the tracker, red for the model, the red line is straight, the blue line is above it slightly here and above it slightly there, but otherwise is on the line. That slight variation is explained by the car, which would experience frictional forces in the wheels touching the ground, the axles rotating in the motor, and air resistance, in addition to the potential of the driver accelerating, which would explain the constant velocity. So those will be the forces acting on the car. The axis position doesn't really matter. I can move that wherever I want, and the slope, as you can see, remains the same, even though the numbers here are slightly different. The slope is in fact the same, so I just put it over here so that all my data will be positive, which is what we want. And then I can say that the net force is 0 because of the acceleration of the car, the potential acceleration of the car, counteracting any frictional forces or air resistance forces, or the fact that those forces would be so small that over this short time period of 0.5 seconds, the frictional and air resistance forces would be negligible. So as we can see, the model correctly predicts the actual motion of the car, and in that their graphs are identical over the time, and the position of the origin does not matter. So that's pretty much it. Anything else? Yeah, I mean, the model matches the recorded observations. Oh, I used this brick as a calibration for the size, and Google Spreadsheets with the linest function to calculate the linear regression there, and yeah, it's pretty good. So less than 20 or less than 1/25 in error, 4 parts out of 100 errors. That's also very good. And yeah, it's all That's what it means, is that it's got 0 net force because everything's canceled out, and so it moves at a constant speed as shown by the slopes, and the speed predicted by the model is the same as the one we actually calculated.